Alright guys, what's up? Today we're going to be talking about water potential. And water potential is one of the most misunderstood things about biology. So it's good that we go over this sort of stuff. So let's get started. If we had a container and then we put aqueous solution in it, and then we had a cell with a higher concentration and there's a semi-permeable membrane between the two, then the cell will increase in size as water rushes in. And water rushes in order to equalize the solution between the cell and the solution outside. And so that process is the basis for water potential. And water potential is symbolized as psi, the Greek letter psi, and water potential is just the potential energy of water to move across a semi-permeable membrane. So what does that mean? So if we take a look at this bucket, we see that water is rushing in. Now what's moving is the water on the outside, which means that all the water on the outside has the potential energy to move in. So that means that the water on the outside has a high water potential and the water on the inside has a lower water potential. So as a general rule, water moves from a higher to lower water potential. Now there are lots of different factors that determine water potential of a solution. And we can spend lots of time talking about, how these different factors influence water potential, but there are two important ones that you need to know for biological systems. And that is with this equation here. Water potential is equal to pressure potential plus solute potential. And those other factors that we showed, they're not as important, but pressure potential and solute potential are pretty important because they influence water potential a whole lot. Now first we'll talk about solute potential, psi sub s. And it can be found using this formula, which is a variant of what's called the Van Hoff equation. And the variables in this formula are I is the Van Hoff factor, and that is a measure of ion dissociation in a solution. We've talked about the Van Hoff factor. You should just know that for organic compounds such as sugars, the Van Hoff factor is equal to 1. Next one is C, and that is the molarity of the solution, and we've talked about molarity in another video. Molarity is just moles divided by liters, and it's measured in moles per liter. Then we have R, which is the ideal gas constant, and we also talk about R in our ideal gas law video. And one accepted value for the ideal gas constant is this, 0.0821 liters atmospheres per mole Kelvin, and it's just a widely used value in chemistry and physics. Then we have T, which is just the temperature. It's measured in Kelvin, so it's an absolute scale. So for example, in this system here, suppose that the solution outside of the cell is 0.8 molar of sucrose in the water, and then we had a temperature of 298 Kelvin. Well, then we can just use our equation here, -1, which is because 1 is the Van Hoff factor for sucrose. Then we had times 0.8, which is the molarity of the sucrose, times 0.0821, which is the ideal gas constant, times 298, which is the temperature. And then we multiply all these out and we get negative 19.57 atmospheres of pressure. Water potential and solute potential and pressure potential are all measured in pressure, or atmospheres or pascals or megapascals or whatever. So for these examples we're going to be using atmospheres. So the solute potential here is negative 19.57 atmospheres. So if we looked at the cell itself, what's inside the cell, the solution there, suppose we had 1.5 molars of sucrose and then 298 Kelvin. Then we use our equation again and we get negative 36.69 atmospheres. So the solute potential in the cell is negative 36.69 atmospheres. But solute potential is not the only thing at play. We also have other forces, like, for example, atmospheric pressure. And atmospheric pressure can determine whether water will move into or out of the cell. So if we place this container out in the open air, we would notice that the atmospheric pressure is pressing down on the water at a pressure of 1 atmosphere. This is not a pressure based on solute concentration. It's actually a mechanical outside force that is acting upon the system. And so any forces like that, we call these a pressure potential. So the pressure potential of the solution on the outside, since the atmosphere is pressing down on it with a force of 1 atmosphere, the pressure potential is 1 atmosphere for the solution on the outside. So now that we know the solute potential and the pressure potential of the solution on the outside, we can add them together to find the water potential. Now in our cell, the pressure potential is actually very close to 0 because there isn't really any force that is trying to push water out of the cell. So the pressure potential is about 0. So if we already know the solute potential and we know the pressure potential is about 0, we can use that to find the water potential is negative 36.69 atmospheres. So we've calculated our water potential for both outside the cell and inside the cell. And these are our values. Now, remember, water always moves from areas of higher water potential to lower water potential. Since the outside solution has a high water potential and the solution on the inside has a lower water potential, water will move into the cell. Now remember we said that the cell has a very, very negligible pressure potential, about 0, because there aren't many forces that are trying to force water out of the cell. Well, plant cells work a little bit differently. Plant cells actually have quite a significant pressure potential. That is because the cell wall of a plant cell is very rigid, and the rigidity of the plant cell keeps more water from coming in if there's already a lot of water inside the plant cell. So the higher the amount of water is inside the cell, the higher the pressure potential will be. So if there's a higher concentration of solute inside the cell, water will keep going inside of the cell until the water potential of the plant cell is equal to the water potential of its surroundings. And so whenever the water potential of a cell is equal to the water potential of the surroundings, there will always be 0 net water flow. So it'll be in equilibrium, and the cell size will stay the same. And in plant cells, this state is called turgidity. So that's all you need to know about water potential. I'm Wallace from A3Academy. Please subscribe to our channel on YouTube, like us up on Facebook, and as always, the more you know, the better you are.
Drop down,